In a revealing announcement that could change our position in the cosmos, NASA has reported the detection of the first extraterrestrial signals coming from the direction of Proxima B. Proxima B is the closest known exoplanet to Earth, located just over 4 light-years away in the habitable zone of its star, Proxima Centauri. This discovery has generated a wave of excitement and curiosity worldwide. Could this be the moment when humanity discovers that it is not alone in the universe? The road to this momentous event began with meticulous observation by NASA's powerful telescopes, which have been monitoring distant stars and planets for signs of life. Proxima B has always been a leading candidate in the search for extraterrestrial intelligence due to its Earth-like characteristics and proximity to our own solar system. The signal detected is distinctive and unlike anything astronomers have ever observed before. It marks a possible turning point in human history. The implications of such a discovery are profound. First, it affirms the long-standing scientific hypothesis that life could exist on other planets under Earth-like conditions. Second, and perhaps more intriguingly, it raises the question of the nature of the civilizations that might reside there. Would they be mere microorganisms or advanced beings, possibly capable of interstellar communication? This signal from Proxima B is not simply random noise or a natural cosmic phenomenon. It carries a structured repetition that suggests an intelligent origin. NASA scientists, along with international teams, are now tasked with deciphering this message, trying to understand its content and the intentions behind it. The global scientific community is abuzz with theories and speculations about the possible content of this message. Could it be a greeting, a warning, or something completely unimaginable? News of this discovery has gone beyond the confines of the scientific community, sparking debates on social media, in government rooms, and around dinner tables worldwide. People are looking up at the stars with renewed wonder, pondering beings who might be doing the same thing on a distant world. How similar or different might their world be to ours? What would their society be like in terms of technology and culture? These possibilities seem as vast as the universe itself. In addition, this detection opens up a number of ethical and existential questions. How should humanity respond if the signals really come from intelligent beings trying to communicate? What protocol should we establish for interstellar diplomacy? And most importantly, how would such a discovery change our understanding of religion, life, and our very identity as human beings? While excitement is growing, there is also palpable weariness. Scientists at NASA and other space agencies are working diligently to validate these findings, ensuring that the signal is not a false positive or a misinterpretation. We are on the brink of what could be the most significant discovery in human history, so the next steps must be taken with precision and responsibility. The world waits expectantly for more detailed analysis. The detection of alien signals from Proxima B not only propels our scientific efforts into a new era, but also unites us with a collective curiosity and hope. We could finally be on the brink of answering one of the oldest and most profound questions. Are we alone in the universe? In 2019, a radial signal was detected coming from outer space, specifically from the Proxima Centauri region, 37 light-years away from us. Although it may seem a considerable distance, it is the closest star to the Sun, being 3 times farther away than the third brightest star in our sky. The signal comes from a triple star system composed of the binary pairs Alpha Centauri A and B and Alpha Centauri C, also known as Proxima Centauri. Alpha Centauri A and B, the 2 stellar companions, are relatively close to each other and quite similar to the Sun. Alpha Centauri A shines with a yellow light and is 1.5 times brighter than the Sun, while Alpha Centauri B is half as bright with an orange hue. Alpha Centauri A is slightly larger than our Sun, while Alpha Centauri B is smaller, so our Sun fits exactly between them in size. But where did the signal between these 2 stars come from? The groundbreaking Breakthrough Listen project, dedicated to searching for extraterrestrial communication in the universe, has named the signal Breakthrough Listen Candidate 1, or BLC-1. The project, which has approximately $100 million in funding, has used thousands of hours of observation with state-of-the-art telescopes around the world. The signal was detected by the Parkes Radio Telescope in New South Wales, Australia. This telescope was observing the region of Proxima Centauri, the closest star to our Sun. This signal almost went unnoticed among the vast volumes of data collected over thousands of hours, but the scientists managed to identify it like a needle in a haystack. For the signal to be considered relevant, it must have two definite characteristics. First, it must be limited to a small frequency range, since such radio signals are not created by natural mechanisms in space. Second, the frequency must fluctuate according to the relative motion of the exoplanet with respect to Earth. The scientists had to analyze nearly 4 million individual signals captured by the telescope in Australia. After an exhaustive process of filtering and eliminating unnecessary signals, they found 5,000 distinct signals, among which one stood out. A signal that could not be explained after cross-checking with contemporary radio transmitters on Earth. This unique signal, with a narrowband technological signature, only appeared when the telescope was pointed towards Proxima Centauri and was observed over a 30-hour period. After analysis, it was determined to be Proxima B, an exoplanet discovered by astronomers in 2016 using the radial velocity method, which detects variations in a star's position caused by the gravitational pull of orbiting planets. The star will describe a small circle, and extremely sensitive spectrographs are used by researchers to follow the light from a star. The spectrum of starlight shifts slightly towards blue as it approaches a planet and towards red as it moves away from it. When these shifts occur repeatedly in regular intervals over days, months, or years, it is accepted that the variation in light is caused by the gravitational pull of an orbiting planet. On closer examination, Proxima B turns out to be very similar to Earth, with a radius 1.1 times that of Earth and a mass 1.3 times that of Earth, indicating that it is a rocky world with an equivalent density. However, there are significant differences. The first is the location of the two planets in their respective solar systems. Proxima B is much closer to its parent star at only 0.05 astronomical units, while Mercury is at a distance of 0.39 astronomical units from the Sun. This proximity would make Proxima B an extremely hot planet, but because Proxima Centauri is a dim red dwarf, the planet receives only 60% of the energy that the Earth receives from the Sun, placing it in the habitable zone where life could exist. There are countless unknown planets scattered throughout our universe. So far, we have discovered an impressive 4,935 exoplanets and have recently added 65 new planets to our tally, bringing the total to 5,000 planets. Betelgeuse, currently 15 to 20 times the size of the Sun, falls into the category of stars predicted to undergo a supernova, signaled by its red hue as a red supergiant. While astronomers generally propose that Betelgeuse could supernova within the next 100,000 years, a recent study by Hayuki Cio and colleagues from Tohoku University suggests it might be in a more advanced stage, closer to exploding. However, there are differing opinions on the validity of this conclusion. Cio's team bases their assertion on Betelgeuse's pulsating behavior, regularly expanding and contracting with overlapping overtones. Although they don't predict an imminent explosion, they suggest it could happen within the next 1,000 years, challenging the longer timescales previously considered. The uncertainty surrounding Betelgeuse's timeline has captured the interest of astronomers. However, some scientists argue that stars like Betelgeuse can endure for more than 10 million years, a surprisingly short span for astronomers but astonishingly lengthy for those outside the cosmic realm. In their quest for hints about whether the bright star might become a supernova, astronomers observe changes in the star's color. In ancient writings, people described the star's color as similar to Saturn's yellowish shade, not Mars's reddish hue. This prompts the question, has the star's color changed? If so, it might indicate rapid evolution, suggesting a supernova could happen sooner than expected. This color shift offers a clue about the star's changes, aiding scientists in deciphering celestial events. Whether Betelgeuse undergoes this explosion on schedule or takes its time to give a stellar show and intensify its final act, humanity will have a front-row view to witness the testament of breathtaking cosmic diversity. What would happen if Betelgeuse went supernova? The idea of a supernova appearing in Earth's sky has captivated people's imagination. New simulations help astronomers understand what we might see when Betelgeuse eventually explodes, expected within the next 100,000 years. Though uncertainty remains, Betelgeuse is about 500 light-years away, and recent research suggests a significant star must be within roughly 150 light-years to cause noticeable effects. Around 26 million years ago, an event of this nature may have played a role in an extinction event impacting marine life after the Pine Era. If a supernova occurred in our cosmic neighborhood, closer than 30 light-years, things could get dicey. Although Betelgeuse's supernova is not projected to directly threaten life on Earth, there could be certain atmospheric impacts. The explosion would emit a surge of ultraviolet radiation, potentially leading to a temporary reduction in the ozone layer. However, research indicates that any resulting ozone depletion would likely be minor and brief, with limited environmental implications. Immediately after the explosion, we would detect weightless particles called neutrinos, which are harmless to us. The star would rapidly become brighter, reaching a luminosity akin to the full moon's radiance within 1 or 2 weeks. Betelgeuse's brilliance would then wane over several months, gracing our daylight hours for about 6 months to a full year. As night descends, it would continue to be a visible spectacle for another 1 to 2 years before bidding us a final farewell. Unfortunately, Orion would forever lose its red sparkle, a twinkle etched into memory. Regarding the threat to humans, supernovas release powerful particles known as cosmic rays, which can penetrate Earth's magnetic shield. However, except for the closest supernovas, the amounts would be relatively minor compared to other radiation we encounter. The supernova's dazzling finale wouldn't just captivate us. It would also produce radioactive iron, a cosmic signature found in Earth's ocean floor and even gracing the moon. This iron, born from a supernova blast 2 to 3 million years ago, was a mere 300 light-years from us. Fortunately, its proximity posed no major threat to life on Earth. Rest assured, such a nearby stellar explosion is a rarity, possibly occurring only once in a billion years. As speculation surrounded the potential appearance of a Betelgeuse supernova from our planet, astronomer Andy Howell from the University of California wasn't content with mere back-of-the-envelope calculations. Seeking precision, he enlisted the assistance of 2 ex-graduate students, Jared Goldberg and Evan Bauer. Their intricate simulations vividly portray the star's epic finale, acknowledging uncertainties while leveraging insights from observations of supernova SN 1987A, the nearest recorded instance of a star's explosive demise in recent centuries. These astronomers concluded that life on Earth would remain unscathed, but the cosmic spectacle wouldn't go unnoticed. According to Goldberg and Bauer's findings, when Betelgeuse ignites, its radiance will resemble the gentle glow of a half-moon, shining approximately 9 times fainter than the brilliance of a full moon. This mesmerizing radiance is projected to grace the skies for over 3 months. Recent studies indicate that Betelgeuse is approximately 724 light-years away from us, securely outside the potential danger zone. Nevertheless, the supernova could have intriguing consequences for Earth. Howell highlights that many animals rely on the moon for navigation and may be disoriented by additional bright objects. Astronomers themselves would face challenges, as the intense brightness would outshine telescopes and space observatories. To adapt, telescopes would need to capture the subtler, softer glow. Experts reassure the public that there will be sufficient warning if Betelgeuse defies expectations and goes supernova during our lifetimes. Earth's instruments would pick up signals like neutrinos or gravitational waves produced by the explosion, giving us a heads-up as much as a day before the event. Although this event is not likely to happen for another 100,000 years, Betelgeuse will eventually turn into a supernova, and the outcome depends on the materials that remain after the grand finale. We await Betelgeuse's potential supernova, as scientists continue to refine their predictions and enhance their understanding of such stellar phenomena. Observations of similar stars in different stages of their evolution provide crucial data for modeling the life cycles and eventual explosive end of massive stars. This data helps astronomers assess the frequency and impact of supernovae within our galaxy, contributing to our broader comprehension of cosmic events and their implications for both nearby and distant celestial bodies. The study of Betelgeuse and other supergiants also aids in the calibration of cosmic distance scales. Accurate measurements of such stars' luminosity and behavior help refine the methods used to determine distances to far-off galaxies, thereby improving our overall mapping of the universe. Additionally, supernovae serve as vital probes for understanding the synthesis and distribution of heavy elements such as iron and nickel throughout the cosmos. These elements play a crucial role in the formation of planets and life as we know it.